Okay. Good morning. Um, before I continue, I just would like to explain again why I'm doing what I'm doing. So I've been going through all kind of things having to do with the second law of thermodynamics, entropy, probabilities, and moving towards the on-cycle relations that I'll discuss today. But in the end, the reason why I'm doing this is because mainly well in the next week I'll be discussing simulation techniques that really start at the microscopic level, where we would like to have tools to compute some of the quantities that play a role in active transport. And so I will not be talking about the kind of things that you have been hearing during the past few weeks, where you model entire systems of active particles, where the activity is already uh, where the origin of activity is already implicitly known, and you just say, well, there's a coefficient alpha, for instance, that tells you something about how they react, and a coefficient mu that tells you how they respond to the presence of a gradient due to another particle. Instead, I would like to know, can I predict these numbers? If I know the molecular nature of the materials, can I predict the numbers? Actually, I will not show any specific example where we do predict the numbers, but I will discuss the techniques that in principle you can use. And so all this thing about talking about fluxes and non-equilibrium thermodynamics, etc. And today I'll also discuss the statistical mechanical uh, equivalent, or if, of a version of that is linear response theory. In the end, is all aimed at obtaining expressions that are manageable if you want to compute something. So um, let me then briefly uh, summarize where I was uh, where I stopped yesterday, and I basically said that if you look at a system that is characterized by a number of control parameters, that could be so you may have a larger system, and a subsystem may have an energy that could fluctuate, number of particles that could fluctuate, so quite a few parameters, and I wrote these parameters like this. And this is not, so for instance, this could be the energy, but it's not the energy itself, it's the deviation of the energy from its average. So uh, the average situation would be that all these alphas are zero, and then what I wrote is that you can write this as minus 1/2, and then some ij. So you start expanding the the probability around its maximum. So the linear term vanishes by definition, because you start at the situation with the maximum probability. You get the next term, which gives you a Gaussian form, and you ignore all higher order terms. And the one thing I also said yesterday is, this is usually a reasonable approximation, but there definitely are situations, for instance, close to a critical point, where you shouldn't believe this. Um, Now, once you have an expression like that, uh, you can start. You can make statements about uh, the well. First of all, the what it means to have a fluctuation in a particular quantity, and secondly, how things will return to equilibrium. But the one thing I would like to say at this stage is that, although I write here entropy, and I expand, I mean, so that I write in S and I expand like this, in principle you can say that I really only am talking about probability. So I expand a state, a system, the probability of find a system in a particular state characterized by a number of independent control parameters, uh, and I just go to lowest order, which in this case is the Gaussian approximation. Uh, it doesn't have to be entropy. So you could well imagine situations that are not described by thermodynamics close to equilibrium that could be described in exactly the same way. Okay, so with that, the uh, the important thing, of course, is that um, if you bring a system out of equilibrium, and now I really will uh, use the language of thermodynamics again, then the entropy will change, and so um, it it might look like this, that you have the S, the alpha I times alpha I. So alpha is already itself a deviation. I forget higher order terms as always. So this is the lowest order. Uh, that is the increase in entropy. Must be an increase because you're going up. Sorry, it must be a decrease. The decrease in entropy, if as you go away from the most probable state. And if you what I did yesterday, sorry, this is a plus sign. Sorry, because the curvature is negative, but I wrote it yesterday as minus 1/2, just out of a notational laziness that actually is not my own invention, but I happily accept it. Um, you write it like this. So this thing is actually minus the second derivative matrix of the entropy. So if you do that, then it means that that the variation in S you can write well simply by saying, okay, I use this expression and differentiate with respect to alpha I, and I get that this is equal to minus sum j g I j alpha j. And so the and that sorry and that is sorry that is ds, the variation of S with parameter alpha I. So S goes down, and this is the way it is described. Now, the key assumption that you make if you're close to equilibrium, and the key assumption that later on will return if we do a simple version of linear response theory, is that if you perturb the system like this, so you have changed a parameter alpha I, or, and this is what I mentioned last time with Onsager, if by some fluctuation alpha I has obtained a non-zero value, then you expect that the system will go back to equilibrium, and so you get an equation for alpha I dot, the time evolution of alpha I dot, and we call alpha I dot Ji. It is the flux corresponding to the rate of change of alpha I, and the assumption is that this is linear in the driving forces. And so normally you would say, well, if I, for instance, perturb the energy, I get the heat flux, or if I perturb the concentration, I get a diffusion flux. But what this equation says, and I've now used the Einstein summation convention, so this you should sum over all J. What this says is that all perturbations of the correct symmetry actually can contribute to this flux. Now this is something I did not yet mention yesterday, but in order to have this kind of coupling, things should have the same symmetry. So for instance, if you have a system where uniformly you have perturbed chemical equilibrium, so the system, for instance, it should be a reaction where you go from, I don't know, H2O2 to the split form where you have 2OH. Then if you have perturbed that equilibrium, then that is something that is effectively, if it's uniform as a scalar, it cannot result in in a vectorial flux. So the thing is that not all driving forces can cause all kind of fluxes. Another example is that if you have a flux that is vectorial in character, so say for instance the heat flux or the diffusion flux, that cannot couple to a momentum flux that is a tensor. So I mean, under certain situations where you break the symmetry of the system, it can couple, but in a homogeneous bulk system, it's not. So there are certain constraints on what you can couple to what, but I mean, in the specific examples that I will be discussing, this will become fairly obvious. Now, the the other thing uh, that I mentioned before is that I had an expression for the entropy production of the system. Uh, Sigma, which is the entropy production per unit volume, and that was equal effectively to now I have to make sure that I do it correctly, to Ji uh, and then Xi. So in this case, it is really the product of the flux of type I and the corresponding thermodynamic force. So yesterday I showed example where this was the heat flux and this is the gradient in 1 over T. This could be the particle flux and this was a gradient in mu over T. Or if we rearrange terms, this would be the gradient. It would be 1 over T times the gradient of mu at constant temperature. So this is the kind of expression that you get for the entropy production. And we can now write this down because we have an expression for J, and if we do that, then you see that the expression for the entropy production is Xi Lij Xj, and so again Einstein's summation convention. So this is the overall expression that you have for the entropy production, and it's a nice quadratic form. But the thing that Onsager showed, and that I will try to show today in two different ways, is that this transport coefficient Lij, the one that relates the flux of type I to the driving force of type J, that's actually a symmetric matrix. And you think, oh, so very nice symmetric matrix, but it turns out that in a number of cases that is very advantageous if you want to compute something. That sometimes the one particular flux is much easier to compute than the other, and so this is why it's not unimportant. So how do we get there? So the first thing to note is that if I look at the following quantity, I have a system that has, well, I mean, alpha I is this fluctuating quantity that tells you how much a particular quantity, this type, is away from its average value. And if I correlate it with xj, which as we now know is the consequence of alpha I as being non-zero, then this actually becomes quite simple. And the way you can do that is the following. You say, well, what this really means, this expression, is that I have an integral over all sets of fluctuations, so alpha, and then alpha I, and then this, where's the x, where, okay, sorry, I have not, did I write well? Did I manage to actually not write the x explicitly? Basically, this thing is the x, but I will write it. Sorry, xi. So I should write it here explicitly, because it is. Now I have to make sure that I don't make a mistake, but effectively it is. Well, let's write it explicitly, and then we can always see later on what's going to happen. The alpha j, maybe I'll mess it up a bit. So this is xj, and then we have e to the power minus 1/2, and now I use my gij alpha I alpha j expression, but then actually what I should do here is also to be consistent and to write here that this is actually equal to minus the well, gij alpha I alpha j d alpha j. So that is the, well, of course the gij is a constant, I can take it out, but that's basically what I've done here. Now the thing that is important is that you can see that actually this means that I have the set over alpha, alpha I, and then the log of this distribution function, the log of this thing, e to the power, this is getting too close. Now even my handwriting has no space to develop. Um, so I get alpha I, and then we get d log e to the power minus, well, 1/2 gij alpha I alpha j d alpha j. It is a bit clumsy to write it like that, but I times e to the power minus 1/2 gij alpha I alpha j. And of course, if I take the log, then basically um, I I just cancel this term. So in the end, what you get is that the whole thing gives me that alpha I xj is equal to, and now I get again. Sorry, I made another terrible omission. I realized there's always a 1/k, the Boltzmann constant. Of course, because S is k log omega, S is not log omega, so I pretended that k equals 1, but that's not true. Sorry, so, and that probably comes in here as well everywhere. Not with the G, but everything else. Good. So then I get that this thing is equal to k, and then we get integration d alpha of alpha I, and then the derivative of this probability distribution d alpha j, and then the only thing I do now is partial integration. So I integrate this, well, let's say the limit on alpha I could be from minus infinity to plus infinity. Of course, at the boundaries, so you get k alpha I p alpha, the whole set I, at minus infinity and plus infinity, but of course there the p vanishes, so this is 0, and then you get minus k times the integral, and then it is the set, and then d alpha I d alpha j, and then times this p. Now the thing is, alpha I and alpha j are independent, so this is delta ij. So it means in the end that this thing is equal to a Kronecker delta. So this is very useful for what we do in a minute. And actually, yes, and it has a, and it does have, sorry, there is, now I have to be careful because now the Boltzmann factor is still there, and the minus sign that I just got here from the partial integration is still there. So it is equal to minus kb delta ij. So that is what we will need. The next thing that we do, and now we're almost done, but it is a bit subtle. At least I find it a bit subtle. I should always draw my understanding curve on the left to indicate that things that in the past I thought were simple now sound subtle to me. So we have this expression, and so I write that if I do that, then I can now do the following thing. I can write, for instance, alpha j, and then correlate it with ji. But I know that ji is given by the by these transport coefficients. So I can write this as alpha I, and then Lij xj. And do I do this? Oh, sorry. Yes, alpha j. Yes, not I here. And this is. Yes, sorry. This is right. No, sorry. I have to be careful because yes, this is Lij xj. That's right. Yes, this is what I want. Lij. And I correlate it with alpha j, and this is xj. This is a number, I can take it out, so this is Lij. And this is apart from the minus kb, this is minus kb times the delta function. And so, um, but I mean, actually, it just means that this was already alpha. So if this would not be alpha j and xj, there would be nothing. But the delta function just makes sure that you only get a minus kb out here. Okay, so now we have an expression because um, the you have an expression for the correlation between the fluctuation in quantity j and the flux in quantity I, and it is related to this transport coefficient. And now what I'll do next is very curious, because I'll say, well, the flux in quantity j, sorry, alpha dot j is what I normally would call the flux in j, quantity j. And so rather than writing this, I write this thing as the integral of alpha dot j and ji. And now, of course, once I've written this as a time derivative, it basically means that I have to explicitly include that this thing now depends on time. So otherwise it is meaningless. So I write it like this. And then what you get is that the whole thing. Sorry, do I do this right? I'm now not convinced by my own notes. This always happens in front of a blackboard, that you suddenly don't believe your own notes anymore. Let's see where it gets me. The main thing is that that you can therefore write this as the integral 0 to infinity j, the current of j at time 0, the current of I at time t dt. And sorry, I put a t here and a 0 there. I'm not yet there. So this is what you can write. And the reason for not writing this but writing that is the following: that later on, when we look at the microscopics, typically, if you look at the correlation between something like this and that at equal times, these things have different time symmetry, reversal symmetry. So if you look at it from a mechanical point of view, you say this is 0. If you look microscopically, then basically it always means that you average over a certain time, you integrate over a certain time, and then there will be a flux as a consequence of the perturbation in the system, and it is that correlation that you're picking up. So basically, in irreversible thermodynamics, you always say a temperature gradient creates, say, a heat flux, and you say that happens instantaneously, or concentration gradient gives a particle flux, happens instantaneously. But actually, it doesn't happen instantaneously. It typically requires a microscopic time to build up. And if you later going to do microscopic calculations to compute things, you need to take into account that this correlation is not immediately established, and that is why it is better to use something where you use alpha dot, so the fluxes that have the same time reversal symmetry, and then integrate, rather than use this thing that actually microscopically becomes ill-defined. Yes? No, you're not the only one, sorry. Sorry. This one? This? Yeah? Sorry. No, at this point it is alpha. And the... Oh, sorry. No, now I totally agree with you that... I mean... yeah, the step that I took actually was more or less like this. I said, I write this, I write alpha j as the integral from 0 to t and eventually to infinity of alpha dot j. This is what I did going from here to there. So this is, I mean, this is just a definition of the flux, and then I replace this expression by the integral. I just replace alpha j by the integral from 0 to t of the flux. That is the way this was created. Is it? y- Well, that's the point. In irreversible thermodynamics, basically you say you have a particular driving force, and so basically you have brought the system out of equilibrium because somehow you've done something, you brought the system out of equilibrium, and immediately you have this flux and you just correlate the two. But if you look at the microscopic dynamics and suppose that let's say that this is the deviation in the energy of the system. So you have perturbed the energy of the system. This is the heat flux. Uh, the energy fluctuations in time typically well, I mean the correlations. So you have a certain energy deviation, and it will both in forward and backward in time regress like that. But the heat flux that results will basically it responds only after a while. So it will do this, and then of course decay again. And in the other direction, it would do this and decay again. So the equal time correlation function of these things, if you look microscopically, is always zero. And that's why the thing that makes eminent sense in thermodynamics doesn't make sense once you go to the microscopics. But we come back to that because when I do linear response theory, it will be more obvious why you have to do this. Yeah, yeah. No, no, absolutely. I mean, green Kubo come. I mean, this is green Kubo before green and Kubo. Now uh, no, so sorry. Now this expression is by now so messy that even I can't read it. So I'll just erase it a bit. So what I done is I had integrated. I started here with alpha j. I integrated this. I have this j of I 0, and this is integrated over time. Infinity is a bit strange. What does infinity mean? It means anything but infinity. It means basically, I don't know whether you is not for infinity, it's eternity. You know this famous Woody Allen quote. Eternity is a long time, in particular towards the end, and that's here also true. Really, this is infinity in the sense that it's a time that is long enough that everything microscopic has happened and everything macroscopic hasn't happened yet. So all the slow hydrodynamic variables haven't changed substantially, but everything microscopic enough to actually set up the transport that you need has happened. So that is this expression, and um, the only thing that we're going to do now is to say the following. Well, first, so I have this. Let's just look at this correlation function j of j at t, j of I at 0. Now the first thing you can say is, and this is, by the way, only true for classical mechanics, but we talk classical at the moment. This is equal to ji of 0, j at t. Nothing has happened. I just changed the order, which classically is totally allowed. Now I do something else, and I say that if I look at fluctuations in the system, and let's I mean, take for instance here the quantity j of I that is fluctuating in time, and here I should use another color. Well, finally I can use another color, j of j that is also fluctuating in time, and I'm computing the correlation function. That basically means that for any time difference t, I take the product of this thing, and that I do for many different time origins. So this is, well, if this is time interval that I'm looking at, for instance, this one times this one, etc., etc. So you take all these products and you do this many times. But the important thing is that so then you get this correlation function. It tells you how the fluctuations in the current in I correlate with the fluctuation with the current itself on average 0. So the current itself is a fluctuation. How it correlates with the current in J sometime t later. But what is important is it doesn't depend on the time origin. So if you have a system with fluctuations in equilibrium, I can measure it today, I can measure it tomorrow, it's the same thing. So it means that this thing is the same as ji tau j tau plus t. It doesn't depend on tau. And so in particular that means, and the fact that it doesn't depend on tau is that if I take then the partial derivative with respect to tau, that should give me 0. Now let's look at what that is. It just says dot j I tau, sorry, is that all? No, sorry, that's not what I want to say now. It is true what I say, but it's not what I wanted to say. No, I want to say something much easier than that. No, sorry, yes, I do. Actually, do I? Now I actually, sorry, I think that no, I don't. I really don't. Let me just draw this time correlation function of I and j, and because they have the same time symmetry, time reversal symmetry, a thing looks like this. And because it looks like this, because it's symmetric, I can move the argument to the other side. Sorry, that is the thing that I'm using at the moment. So, and actually, if the time reversal symmetry would be different, I could also move the thing to the other side, but I would have to put in a minus sign. That sometimes occurs, but in this case, the situation we look at that now, that is not the case. And so, because of that, this thing is equal to j of j at 0, j of I at t. But that integral, and now we go all the way back to what I had nowhere, or so maybe by now erased. Is it still somewhere? Have I not even given the final result? That's an interesting one. Sorry, I have to desperately look for where I somewhere should have written the expression that relates the transport coefficients to the okay. Otherwise I repeat it. I must have in my eagerness to erase everything to have erased a key thing. I apologize for that. So the main thing that I needed is that the integral from 0 to infinity ji 0 j of j at t dt is equal to Boltzmann constant times Lij. Now, because I can move this from here to there, because it has the same time reversal symmetry, it is also equal to kb Lji. And that is the Onsager relation for in cases where the fluxes have the same time reversal symmetry. If they have opposite time reversal symmetry, you get a minus sign here. Sorry? Okay. I'm sure it is a minus. Where was the minus? Here? Oh no, sorry. Tell me where I should put. I'll put a minus wherever you say. So sorry. Yes? That's a minus sign, yeah? I should have the same minus sign on the left board, and indeed in my equations it was there, and then I let me see what I did. I cunningly got rid of the minus sign, and I have to see how I did that. Okay, so this is what's called a blackboard. No, oh sorry, I'm very sorry. I now see what I wrong-footed myself, and thereby wrong-footed all of you. So I let me see where I have to backtrack, but the main thing is that I did have the expression alpha j at t, j of I t is equal to minus kb lij. And what I did then, and there now, so here I said um, I integrate, um, and so actually this you in this case I actually write this thing as an integral, and so I write this as dt prime, and then I write it as alpha j, still the same alpha j. I shift the time origin, but I do j dot of this, and then I move the dot, and so I knew that I needed the fact that this was time invariant, because when I move the dot from here to there, then I get this minus dt, and then you get ji 0 ji j of t, and then the minus sign here, mysterious or not mysteriously, has changed to a plus sign, and then everything is okay. So sorry, that was the thing I did wrong. Yes. Or another mistake, maybe. Yeah, yeah. No, no. So no, because if you look, this is alpha j, and this is xj. So the delta is taken care of. If there would be an other index, it would be a problem. But this is just to pick out that aspect. So if I have a flux in I due to j, and I correlate it with alpha j, then you get something, and otherwise you get nothing. Okay, so far so good. Not very good, but a bit good. So the main thing about the thing that we now have is that, do we have it still? I should at least write it down somewhere for future reference. Is that we have an expression that relates these transport coefficients. And remember, these transport coefficients really tell you something like how does diffusion change if you apply a temperature gradient, or that we have the expression that 0 to infinity ji 0 j of j t dt is kb lij, and that is also equal to kb lji, unless the things have different time reversal symmetry. So this is the thing that we get from these quite general arguments about the Onsager-style arguments about fluctuations, how fluctuations regress back to equilibrium, and that you assume that this is exactly the same way in which if you have a system perturbed, how the perturbation relaxes back to zero. Now, just to take a bit of an advance on what's going to happen later, so what would be these things be? For instance, let me just take one example. Suppose that we want to compute the coefficient that determines how the heat flux responds to a temperature gradient. We usually call that thermal conductivity, although in this particular case, the way I've written it, where I take the gradient of 1 over t rather than t, there's a factor 1 over t squared. But basically, what you need is an expression for in that case, you would relate the thermal conductivity coefficient to a quantity that correlates the heat current at time 0 with itself, but at a later time t. And so, just to give you an idea how microscopic that looks, so the heat current density, I think you typically divide by the system volume, and you get something like this: 1/2 mi vi squared. That is so this is a v, this is not a nu. Okay, just plus potential energy phi times the velocity of particle I. That's the and then you'd think that that's all, but actually it's not, because there's a second term that looks like this: Vij Fij. I should add that this is if you have particles with pairwise additive interactions, and then Rij, the vector separate R. and this is summed over J, and this whole thing was summed over I. That is the expression that you would have for the heat current, heat current at time t. So if you want to know the heat conductivity of a system, you have to compute the correlation function of this thing. So there's here you see the energy of a particle. Mind you, what is this? The potential energy per particle. It's actually a bit ill-defined, because if you have pair interactions, and then typically you say, well, the interaction potential may be Vij, and what you do in this picture typically is to give one half of that potential energy to particle I and one half to particle J, which seems somewhat arbitrary, and actually it is. For bulk thermal conductivity, it makes no difference. What happens close to a surface is a bit more painful, because actually it's not completely obvious um, how to deal with it correctly, except for just pretending that it's the same as in the bulk. Okay, so you have here the kinetic energy of a particle, potential energy of a particle, and this is almost like if you look at it, it is something. If you're familiar with the virial, it looks like something that tells you how the virial of a particle changes due to motion. So it is something that tells you how particles moving relative to each other, Vij, how they actually can also transport work. And so what does it mean? It basically means that if I have a fluid, let's take hard spheres, because as you know, Ludovic said it yesterday, I like hard spheres. How can you transport energy? Well, you can transport energy by just moving the sphere, or you can transport energy by doing this. And that basically is this term. So this is just an example of a typical quantity that could appear in these correlation functions that play a role in in all transport phenomena, but in particular later on when we talk about phoretic transport. Now the next thing I'm going to do, I forgot to start my clock, so I'll have to watch the time. The next thing I'll do is to do the same thing, but now starting really from microscopic. So for the time being, I'm done with yes. Sorry, here, yes. This is Ri dot minus Rj dot. So you have particles in the system that interact. This is particle I, this is particle J. This is Rij. Of course, Rij is a vector, so I have to define which way it goes. And Vij is, so this is Rij is Ri minus Rj. And Vij is Vi minus Vj. And Fij, well, I mean, in this case, for pair potentials, you have actions equal reaction. So you get basically, it's the force on particle I due to particle J. And so you can, I mean, there's not much point in separating it more. So as you know, Newton's third law is action equals reaction, but there's a general principle, I think, that third laws are never quite the same quality as the others. It's the same for the laws of thermodynamics. Third law is okay-ish, but it's not so great as the first two. Point is, action equals reaction is perfect for what Newton was trying to achieve, namely looking at gravity, which is, as far as we can tell, at least in the classical picture, simply describable by pairwise interactions. If you look at many body forces, and people who do electronic structure do that all the time, and people who do density functional theory, even classical density functional theory, do that all the time, then this whole statement is pointless. There is no Fij. You cannot say that the force on particle I, you cannot decompose it into forces due to other particles. You can do a lot that comes close, but not quite. So, but I will just, for simplicity, focus on the situation where you have pairwise additive forces, and then you can do this. Have I explained all terms? I'm not sure. Yes? Sorry. Yes. I mean, well, okay. So the heat flux, and I have to be a bit careful. if I maybe I'm not sure if I wrote it down, but basically the heat flux, the way people write it, is um, so the heat flux in the x direction. So x. Now I have to do the q up here. It is x times uh, the Hamiltonian of the system, and of course you can write it as a sum of, well, sometimes as a sum of terms, sometimes you can't. But um, now I have to be careful because now I'm afraid that I didn't take the notes with me to that tell me exactly what the thing is, because the point is I think that okay, so I this x I'm a bit concerned about, because clearly what x do I mean here? But in essence, because if I differentiate, you can see that I get a velocity of a particle. So I probably have um, to write it like this. But then the question is how what do I do here? And this to be quite honest, I don't know at the moment. But you can see how in principle, even if the Hamiltonian contains non-pairwise additive terms, something like that should still be valid. And let me give you an argument why you could do this. And it's a bit of a shaky argument, but if you have, let's first look at something much simpler. Let's look at diffusion of particles. Now we know that if you have a system in equilibrium, and I look at the concentration of a particular species, Ci, that all other things being equal, that concentration is constant. If I apply a potential gradient, so for instance the potential is high here and is low there, then you can imagine that you get a concentration profile that is like that. It is still an equilibrium profile. And because we know that this is the Einstein relate, so the way Einstein derived the relation between mobility and diffusion coefficient precisely by considering this kind of situation, where you apply a linear potential gradient, and then you know that the flux due to the force that is the derivative of this gradient must be compensated by the diffusion flux. So this is the way you get the relation between mu, the mobility, and d, the diffusion coefficient. Now, the more general argument that you can use in other cases, you can say, now let's assume that we have also a potential that couples to the energy content of the system locally. You think, this is weird, unless you realize that gravity actually does that. I mean, gravity does more than that, because it also, I mean, typically gravity pulls so hard on but because the energy content of a particle, so kinetic energy and a bit of interaction energy, is usually very small compared to mc squared. So usually the main effect of gravity is to act on the rest mass. But if you now imagine that you have a force that only acts on the excess energy of particles compared to the average, so you look at well, let's say energy. And then I think that you'll be forced at some point to go away from energy of a particle minus the average energy to something that is more averaged in such a way that you can take these many body effects into account. So you really look at the energy density coupling to a field. If you can at least define a local energy density, however imperfectly, then you can imagine that applying a field that couples to this will actually give you a temperature gradient. And so then you can again think in mechanical terms about heat flux. And this is an argument that was used very early on in the early 1960s by Luttinger, who was one of the people who actually followed up on Green and Kubo. And on the whole, I wouldn't say it's been ignored. It has been attacked, in particular by Martin, but he didn't explain why. He said, they haven't understood my work, but that's not particularly helpful. so I also don't know what Martin hadn't understood. But Martin typically follows this line. He says, just imagine that you have a fictitious field that couples to the energy density, and then you can describe heat transport as a mechanical effect, and then everything is fine. But then in practice, the examples he considered, and they were just, I mean, he didn't even work it out in terms of a calculation, but the example were examples where this non-additivity of the interaction didn't explicitly play a role. But I mean, if you want to do it, I'm sure that this is one of the things you'll have to take into account, that you must be able to at least define a local energy density, Otherwise, the whole idea of transport makes no sense. Okay, or not okay. So I mean, actually, you may think that this is embarrassing, but this is what I enjoy because there's a French author, and unfortunately, maybe there's quite a few French people in the room who probably can tell me who the author was. Who made a wonderful statement because he was a 19th century author. He said, "My thoughts are so clear that you can see the mud on the at the bottom." And this is more or less what I try to achieve. That I try to explain to you how far my understanding goes and where it stops. And so that at every stage I'm very happy for your input there. Anyway, so what we're now going to do is to uh, approach the same problem from a statistical mechanical point of view. And one of the reasons for doing that is that statistical mechanics is the natural starting point if you want to do simulations where you actually look at the motion of individual atoms or molecules. And so uh, we first do a kind of step back in time. But what I will first do, well, first of all, I define the system. So I say I have a system that has a Hamiltonian H0 that contains a kinetic part. And the kinetic part, well, I mean, it's kinetic. That depends on the momenta. This sum pi squared over 2mi, and it has a potential part, and that is whatever it is. It depends on the coordinates of all particles, and I will use the symbol Rn to indicate that it depends on the coordinates of all particles. In many practical cases, this may be pairwise additive, but at the moment I just assume nothing at all about it. And then we can compute the average of some observable quantity. It could be the energy of the system, the total internal energy. It could be the pressure. It could be, whatever, dipole moment, dielectric constant, things that you can measure experimentally in equilibrium. And that would be if we now go to systems at constant temperature, constant volume, number of particles. That would be equal to e to the power minus beta. Sorry, but beta is 1 over kT times the Hamiltonian, which depends on all these p's and q's. And I apologize. I mean, I said it's all n. Whenever I write here p and q at the moment, I actually mean that there's an n. So this is all the p's and all the q's, but that is on a slide I would have done it, but when I do on the blackboard, I'm too lazy. This is my observable quantity that also depends on all p and q, or usually it doesn't depend on all, but on some. I don't repeat the arguments, and of course this is integrated over all phase space coordinates, which I denote by gamma. So that is all the p's and all the q's. Now, okay, so this is nothing new. This is more or less statistical mechanics 101. And now the first thing we're going to do, and then I'll have my 5-minute break, is to say, suppose that I have this system and I have the Hamiltonian H0, and I add to the Hamiltonian a small perturbation, and for practical reasons I'll give it a minus sign. And this perturbation has a coupling parameter and some quantity b that in principle again can depend on all the momenta and coordinates in the system. But the way I do that is the following way. I say I want to look at the system at this time t equals 0, and I switch on my perturbation at t equals minus infinity, which is a long time ago, and then I look at how, for instance, another observable A, which I have written down here, how that observable A changes. So I look at delta A. And if I look at delta A, initially, of course, I was in equilibrium, started here. You wait for an infinite amount of time. It equilibrates. And you have a finite value of delta A here. So that is the first thing. Later on, we're going to see what happens after this. But at the moment, I'm just looking at what happens once you have reached equilibrium. because I'm so that's the static response of a system. Now, uh, so in order to look to see that, we just take the same expression as we had before, but now we take it with a small perturbation, e to the power minus beta h0 minus lambda b a, and now I leave out all the arguments, d gamma divided by e to the power minus beta h0 minus lambda b. And now we say, for very small lambda, I can write a of lambda is dA d lambda at lambda equals 0 times lambda plus higher order terms which I can ignore. Not always. For instance, close to a critical point, it may be that this linear term simply doesn't exist, that the response is not analytic. But in most systems that are away from critical points, you don't have to worry. So then there is a regime where you can assume that the response of A to this perturbation lambda b is linear in the coupling parameter. And then you can say, okay, let's compute this. So we have to compute this average. So if you differentiate with respect to lambda, you see there's a lambda here and there's a lambda there. So let's do it. So dA d lambda is equal to, well, first e to the power minus beta h0 minus lambda b. I will take the lambda to 0 at the end, so it's still there. Then you get, differentiating with respect to lambda, you get here a plus lambda b times a, and then we still and d gamma, of course, but then we still have to do the denominator. So this is still e to the power. This is just differentiating the numerator. If you do the same thing for the denominator, then what you get is, well, a term very much like this, and the term has a minus sign because I differentiate with the denominator, and so and then so you get minus, and then effectively e to the power minus beta. Well, I should have planned ahead as always, so I have to now desperately think what I'll do. But actually, what I'll do is introduce a shorthand notation that allows me to write the second term more easily. What you see is that this is equal to lambda, and then this is the thermal average of the product AB. So this is lambda AB, the first bit. And then we can really say at lambda equals 0, so in the unperturbed system, because we take this derivative at lambda equals 0. And the second term, if you look, you get one term that is exactly this, and the second term is the derivative of that, and that basically is minus A average 0, B average 0. So basically what you have is that the response of a system dA d lambda due to something that couples to a quantity B is equal to delta A, where delta A is the deviation of A from its equilibrium value, delta B computed to 0. So here you have already something that may be either a cross correlation function or an autocorrelation function, something that tells you how fluctuations in A and B correlate. That tells you how a field coupling to B will change A. And so that is, for instance, if you have, as an example, a system that is polarizable, then the lambda might be a field, so you apply an external field, you couple to the dipole moment, and you look at the response to the dipole moment, and then you would conclude that the susceptibility in that case is related to the mean square value of the spontaneous dipole moment fluctuations in equilibrium. That's just an example of such a relation. Of course, for dipole moments, like an ideal gas in an external field, we can also compute a non-linear response. But here we're just in the initial linear regime, and there it's all very simple. Now we have a 5-minute break, and then I will continue and look at what happens if you do things time dependent. Yes. Oh, yes, yes, yes. Thank you. I forgot the beta. They came down, of course. Otherwise, it makes no sense. Yes. Thank you. Once that's all there, yeah, definitely. Thank you. See, I need you. That's okay. I think I will slowly continue. I mean, by the way, in the first hour, I have been able to illustrate that I sometimes don't obey this inequality. So that's but you keep me straight, so that's fine. Um, so now um, I know the response of a system, and actually it was pointed out to me that, of course, if you differentiate here, there's also a factor beta coming in front, which I totally forgot to write down. So the actual response is this. Now I asked what happens if the system is here. It's totally in equilibrium. I know the equilibrium distribution. It is the equilibrium distribution that corresponds to this term. And now I switch off the perturbation. It's a tiny perturbation. And what you'll find is that at some point that this delta A will go back to zero. So it will start decaying. And then either this or that, whatever way. But if you wait sufficiently long and the system is equilibrium, so it can actually sample all configurations, this system will go back to its equilibrium state. And so the first thing we're going to do is, yes. Oh, sorry, no, the lambda, sorry, oh yeah, I thank you very much. I was mixing up two states. I was first looking at delta A itself, and then it would be multiplied by lambda. Here it is just the beta. Absolutely, sorry. Very good, thank you. You're paying such good attention. That's great. Yes, because of course, once you have taken derivative of lambda equals zero, then it would be very painful if there would be a lambda. Yes. Um, so we look at how this quantity delta A decays to zero, and so for convenience, what I will do is just to pretend that the quantity A is already the difference between A and its average value, so that the average value of A is zero. Otherwise, I mean, it makes no difference except that otherwise I always have to go through this step of subtracting the product of the averages. But um, at the critical moment, whenever it's needed, I can still do that. So the main thing is that you want to know how delta A, or delta A itself, evolves in time for t larger than 0. So for t less than 0, we know what it is, because we know this response, and so if we multiply by lambda, we have delta A at time equals 0. And for larger times, something will happen. And so, can we compute what it is? Well, so first of all, we know, I'll make a drawing of phase space. It's not really two-dimensional, but basically, initially, let's say, assume that phase space was uniformly populated. If we apply a perturbation of the type minus lambda b, then it might have the consequence that some parts of phase space are more populated and other parts of phase space are less populated. So you have perturbed the phase space distribution, but we know exactly how, because it is given by this Boltzmann factor. We're in equilibrium, we know what it is. Now we switch off the interaction at time t equals 0, and from that moment on, all the variables evolve, but they evolve according to the original Hamiltonian, h0. The perturbation has gone. So from that moment on, you can follow the trajectory of the system through phase space. You can take different origins, and over a finite amount of time, you find that there are different trajectories that the system can follow, but they all according to the original Hamiltonian, h0. So the only thing that is affected by the perturbation is the distribution function from which you start. And so if we write that down, basically it says integral, I just write here the phase space variable, exponential minus beta h0 minus lambda b. That was the interaction that was active until time t equals to 0. And then a at time t, given that it was at original coordinates p0, q0. So basically, you compute what a is by saying, I know the original position. This is also the original coordinates. I have to normalize, of course. What did I do? I know the distribution of the original coordinates. To compute a at time t, I only need to know the original coordinates and the Hamilton equation that tell me how a evolves in time. I mean, you can write it down explicitly you do for what the time evolution for a is, but I mean, basically, if a is a function of p and q alone, then this is very straightforward, and you can, I mean, I can write it in a more complicated way, but it's just the same thing. So you start here, you know the equations of motion, so you know how a would be in time t, given that you're originally there. Good. So now we know that, and then we can compute the averages over many possible initial conditions given this perturbed distribution, and we will find that this a will in time evolve, this at least the average will evolve in such a way that at sufficiently long time the value of a goes to its equilibrium value, and so the delta a goes to 0. Now, so again, we can do exactly the same as what I did before, and that is say, let's expand in powers of lambda to lowest order. And if you do that, then you will not be surprised, and I will actually not repeat the argument, but basically it says that delta a at t, given that my perturbation is delta a at time t is equal to beta lambda. Now I take the lambda explicitly, and then delta a at time t, delta b, or actually, well, delta b, yes, yeah, because we wanted to have, otherwise I have to subtract these averages, delta b at 0, and this derivative is computed at lambda equals 0. So it is very much like the static case that we had here, except that now I don't take a at the same time, but I take a at a later time. That's the only thing I'm doing. And The reason why this is useful is not that this is an experiment you do very often, that you switch on the perturbation, switch off. You can do it, but the important thing is that we look at a linear response. And because the response is linear, it means that if I have, for instance, one perturbation like this, and another perturbation that, for instance, is like this, and so it basically, if you can make a sum of all kind of perturbations that you can consider in this way that I now describe, then you can have in general any kind of time dependent external perturbation. So you don't have to have this lambda fixed. It could be time dependent, and still, because the response is linear, you can write it as a superposition of uh, the effect of the individual perturbations. So basically what is going to happen is that we go from lambda, which is a constant, to some function f of t that is variable, and still we expect that somehow the response will be similar. But of course, this f of t is not a step function, so we can't just write this. This is not going to work. So we have to figure out how to do this. And the easiest way to do this is to simply consider the general phenomenology of a linear response. So we write this in terms of a general time-dependent susceptibility. I mean, it's only a word, and the only thing that it says is the following: if I want to know the response of a quantity A to a perturbation, a time-dependent perturbation that couples to a quantity B, then it looks as follows. Ooh. Oh yeah, sorry. It depends on my time-dependent perturbation, because remember now, instead of having minus lambda b, we now have a time-dependent factor lambda b, a time-dependent coupling. So our Hamiltonian looks as h0 minus f of t times b. So it's a time-dependent Hamiltonian. But actually it turns out to be not important, which is, in this particular case, it's not important. So this is the, and then we have a response function chi a b that tells me how A responds to B, and that depends on t prime. Actually, it depends on t and t prime, and there are a few things that you can immediately say. I could have started my field at minus infinity. I could have gone on to plus infinity, but clearly that's not very useful, because there will be no response to any field in the future. So we can, for causality tells us that this is going to depend only on t. So it goes, at most goes to t. The second thing that we can immediately say is, because of time invariance, whether I do the experiment today or tomorrow makes no difference, this can only depend on the difference between t and t prime. So that makes it here a bit easier. And so this is the most general phenomenological. There's no microscopic here at all. This typically say, if I apply a field, then I expect that for every, so you can basically write my external field, you can say it is like this here, like this there, like this here. And for every contribution of the field has its own contribution, and they just add up linearly because it's linear response. Okay. Then I'm just going to consider a specific case, and it will turn out to be a very familiar case, namely the case where f of t, well, let's have f of t is lambda for t less than 0 and is 0 for t larger than 0. Because then we're back to this case, and then we know the answer. So we do that, and then so the first thing that happens is that in that case this becomes delta A of t is equal to, well, still minus infinity. Now it doesn't go to t, it goes to 0, because then we switch off our field. The field is otherwise constant, so we take it outside. It is lambda. And then we have this chi AB of t minus t prime. Sorry, t minus t prime and dt prime. Which actually, if you wish, you can change to the variable tau is t minus t prime, and then you change the variable that this is tau, this is minus tau. You change the integration variables, the order of the limit integration limits. You switch them, and you get that this is equal to lambda t to infinity chi ab tau d tau. So now we have two expressions, because we have an expression here, and there's a lambda in front. So basically, what we now know is that if I take this expression, and then I can equate to the other one. So I basically can write this must be, I really should use the eraser because I have to create space. This is equal to lambda, and of course the lambda will drop out later. T to infinity chi ab tau d tau. Okay, so now we have the general the general response of a system to an external, a small time-dependent external perturbation, because once we relate this one to that one, we can from that moment on compute the response to any perturbation, because that's we have basically, you can get chi itself by differentiating. And so let's do that. So chi ab of t. So then we do that by differentiating with respect to the limit of the integram. But actually you'll see, because it's the lower limit, you get a minus sign, and then you get that this is equal to minus beta, and am I doing this right? For some reason I think it is right, but I suddenly cannot convince myself anymore that this is right. That always. Oh, sorry. This is what I get here. If I differentiate here with respect to t, then I get an a dot. So I get minus b, and then we get delta b at 0, delta a dot at t. So this is the expression we have for the time-dependent susceptibility. And now, because this is all microscopic and could be computed by, say, simulation, we can then predict in general the time-dependent response of the system to an external field that couples to the quantity b. Now we're going to make it a bit simpler, and the way we're going to do that is first to make use of the time invariance. And I already said, so there is a minus sign here, so this is actually important. I started saying, and then I said I don't need it, that a0 bt dot plus a dot 0 bt must be 0, because this is the first term in the expansion of a tau b t plus tau, which cannot depend on tau. So if I differentiate, this must be 0, and therefore this must be 0. So that means that I can just move the dot by changing a minus sign, and so I get that this is plus beta delta b dot 0 delta a at t. Okay, so far so good. And this is actually something that you can use. And so I will give one example that actually I honestly don't like all that much, because it is a bit iffy for a reason that I'll explain. But it shows you how you can get physically interesting results immediately from this kind of expression. And the example that I will consider is that you have uh, a system where you exert a force on a particle. Now this immediately makes it clear why it's a bit iffy. If the system would be infinitely extended and the force would also therefore go from minus infinity to infinity, then you immediately would conclude that the energy of the system is not bounded from below, and then all statistical mechanics can be thrown away. So you have to assume that the system is finite, very, very large, so that actually we don't worry too much about the fact that what happens at the boundary. I mean, typically you could think of a system that very far away maybe has open boundaries, but somewhere in between it basically feels a constant force, so like a potential gradient, and we're just looking at what happens in that regime. So how does a particle move in a regime where there's a constant force? Now, then we say, okay, so in that case, in the regime that we're interested in, our Hamiltonian looks like h is h0 minus fx, the force that acts on particle are in the x direction times x. And so this is the culprit, because this cannot go to minus infinity or plus infinity for that. So this is but I just assume that that's not going to create a problem. And I want to know the average drift velocity of a particle at time t. Now we're going to use the expression here. So in this case, a is the drift velocity, and b was, well, it was the quantity that coupled to the force. So we had minus x times f, and in general we had minus lambda or minus f. No, so let's say minus b times f of t. So you see it looks very similar. The thing is that actually in this case b is x. But then this says that b dot is the velocity. It's vx at time 0. And a actually was the thing we want to compute. It is also the velocity, but now at time t. And so what this tells me is that the average drift velocity, v average x, is equal to beta, and then you get integral from 0 to, and now we come back to this infinity, vx0 vxt dt. And actually this thing is the mobility m, which actually is the diffusion constant over kt. So this thing alone is the diffusion coefficient. You can also derive this in another way that I will not do today. But you can see how, once you know how the velocity of a particle evolves in time, and you sample this many times in a calculation, you have this correlation function. And then once you have the correlation function, you can integrate, and then and then you get either the mobility or the diffusion coefficient depending on what you want. Now the point that I say here, this plus infinity, is the following. If you do the same expression, but you were to start from the macroscopic diffusion equation, you would get something really strange, because what you would find is, I mean, and this is just by equating the expression for the mean square displacement of a particle to the 2 times the diffusion, or in the x direction by 2 times the diffusion coefficient times t. What you would then conclude is that d, the diffusion coefficient, is equal to 0 to t vx0 vxt prime dt prime. That is what you get by simply looking at saying that dx is of if t is equal to integral from 0 to t vx of t prime, and then saying dx squared average must be 2 dt, and therefore if I differentiate an average, you get this expression. But there's still a t here, there's an upper limit, and this is precisely what I said at the beginning. There's this strange thing that I said the integrals have to go to plus infinity to at least to the time scale where this thing has converged. The macroscopic transport coefficient, that this is for diffusion, but it's for all the on-cycle coefficients. You can compute them from microscopic correlation functions, but not by taking equal time averages. That's not going to work. You really have to integrate the relevant correlation function up to a time where this correlation function has decayed. And this is where it comes in, that I earlier in the lecture wrote, and instead of having my alpha j dot, or alpha dot j, whatever it was. Um, sorry, alpha j. I didn't write it. I wrote basically something that in the end contained alpha dot and j dt from 0 to infinity. And now you know what this infinity means. It is you need enough time for this correlation function to decay back to 0 so that the integral has a well-defined value. I think that is almost a good point. How are we doing time-wise, Gerard? 5 minutes. Well, one thing I could do with the 5 minutes is just, I mean, I can do something a bit trivial, but in the meantime you can ask me questions. I can just tell you some of the quantities that you have to compute the to evaluate to compute the better known transport coefficients. So, and of course it is actually quite surprising what linear response theory does. It is a bit like, of course, what Onsager did in a macroscopic thermodynamics way, but what you get here, these expressions, and this is really a Green-Kubo expression. So all these integrals that relate a transport coefficient to integral of time correlation function are called Green-Kubo relations. The original derivation from Kubo is interesting, but in a sense a bit painful because he tries to keep everything quantum. And that is, in some cases it's useful, but in effectively all simulations that you do for these systems, you do classical dynamics, and then it is much easier to take the kind of cheap route that I took to derive the results. There are situations, by the way, where the quantum bit really becomes important. For instance, I said you can compute the response of a system to an arbitrary field as long as you're in the linear regime. So you can, for instance, look at the response of a system to a fluctuating electrical field. And that could be, for instance, a monochromatic field. And then what this system tells you is how the dipole moment of a system responds to a periodic electrical field. And if you then look at the component of the dipole moment that is out of phase with the applied field, that gives you the dissipation. If you radiate a field into a sample and you have dissipation, that means the radiation is absorbed. So you can compute the absorption coefficient of a medium by computing the dipole moment correlation function. That works all fine for microwave radiation, etc. However, if you go to higher frequencies, then the classical description breaks down when h bar times omega, so the energy of a quantum becomes comparable to kT or larger, because then really you have to go back to the original quantum formulation that I will not do, because here we talk all about phenomena that are not in that regime, and so I'm not particularly worried about it. So the final thing I said, what I would write down is the expressions that you have for different important transport coefficients. For instance, the viscosity you compute as integral 0 to infinity of the, well, a off-diagonal component of the stress of the system. I assume it's an isotropic system, where the stress is so this actually looks very similar to what I mentioned before. This is assuming pairwise additive interactions, and there is therefore a bit of an issue as soon as you go away from pairwise additive interaction. But this is the thing that you'll see in most calculations that can use pairwise additive interaction. So if you compute a stress, for which you need the velocities, the particle distances and the forces between the particles, you can compute this correlation function, and you can compute the viscosity of a system. And similarly, if you want to compute the heat conductivity, then it is 1 over v kT squared. The kT squared comes because people take the gradient of t rather than 1 over t as I did, and then integral 0 to infinity. And then it's the time correlation function in the x of the heat flux in the x direction. And that heat flux I wrote down, and as you remember, it had one term that contained the velocity of a particle multiplied by the energy carried by the particle, and the second term that looked like the work you have to do against if the particles move relative to each other, and that was the term that actually transported energy even without transporting particles. So these are the most important ones. There's other ones, but I mean we have already written down the diffusion coefficient. So I think that with these expressions, I would like to stop for today. But if there are questions, I'll be happy to answer if I can. Questions? Yes. Sorry. Yeah.